Hello, Online Beam Summit. I'm Robert Burke, and I am re-recording the beginning of my talk, which was given on September 5th earlier this year, because there was a problem with the audio. So once I've gotten through the prefix of my talk again, it will cut back to the original recording. So please don't be alarmed when that happens. I guess I'm going to take it away. Hi, welcome to Beam SDKs Don't Have to Look the Same, a quick look at an alternative Go SDK design. I'm Robert Burke. I am a Beam PNC member for the Apache Beam project. I'm also a Googler. I work on Google Cloud Dataflow, and my current favorite programming language is Go, which is why I continue to iterate on the Go SDK. Let's get started. But before we really get going, we know what a Beam SDK looks like, right? Let's take a look at Java. You have some kind of way of processing each element as it comes into the worker, some way of specifying things that you can start the bundle with, and finish the bundle with, as like lifecycle methods, some way of accessing a bunch of per element metadata or specify different kinds of callbacks, a way of plugging everything together into a pipeline graph, maybe some kind of convenience functions for lighter weight functions. Bing, bang, boom. Beam SDK. We know what a Beam SDK looks like, right? Let's take a look at the Python SDK. We have some way of specifying a process element method, ways of doing things before and after the bundle, and some kind of lifecycle methods like start bundle, finish bundle, ways of accessing different per element metadata and specifying other kinds of callbacks, a way of connecting it all together into a pipeline graph, and maybe some convenience methods for lightweight functions. Bing, bang, boom, Beam SDK. We know what a Beam SDK looks like, right? Let's take a look at the Go SDK. We have some way of specifying a process element method, kind of registering it for use with the system, ways of doing start bundle, finish bundle, and other lifecycle methods, some ways of getting element metadata and some other handy callbacks, a way of putting it together into a pipeline graph, and kind of convenience methods that you still have to be able to register so that the system's aware of it. Bing, bang, boom, Beam SDK. So one of these things are not like the others, and let's talk a little bit about why that is. So as this talk is focusing on an alternative Go SDK design, let's take a look at the differences of Go between Java and Python. Go famously does not have any overloading, which prevents method overloading, function overloading. It prevents a syntax like PCollection.apply, which ends up requiring certain overloads to be able to function. There's no inheritance. There's less guidance on how to actually specify which of these methods need to exist or can't possibly exist. We need to infer all of this stuff reflectively. Go doesn't have any built-in serialization or pickling of native types. So this prevents kind of closures or reliable functions that are written anonymously. You need to name and register everything so we have for sure able to access it on distributed workers in the framework. We don't have annotations, which add a kind of convenient quasi-lightweight mechanism of specifying, I would like to bind this method to this callback or to this like static data or these fields to this kind of metadata as part of the element. So nothing like that. The current Go SDK needs to do things very positionally as a result. And at the time we wrote the SDK, there's no generics. So we had to make sure that the SDK needed to type check itself. And as a result, that made it very difficult to do things like user-defined iterators. Kind of hard to write iterators without generics. This next slide is covered by the audio, so take it away past me.
But that's no longer true. In Go 1.18, Go finally acquired type parameters, colloquially known as generics, which lets you build up various structures and methods that operate the same way on functions and types generically. Similarly, in Go 1.2.3, which came out 2 weeks ago-ish, as of this recording, there's finally also user-defined iterators, which, as you might imagine, is kind of useful in a structure like Beam, where we're often dealing with various streams of values, like coming from state or from side inputs and similar. So these aspects matter in how you design an SDK itself. It affects how discoverable the features are to users, which also affects how the IDEs will support things, how you will document these things, how discoverable that documentation is by itself. This affects how we add features to the SDK and how much code is required to correctly implement a feature. In order to add a bunch of things to the current Go SDK, I need to change the entire type checking mechanism to support various features, which makes adding or changing features on the SDK side a little bit more challenging than I would want as someone who has to maintain it. It also affects the performance at construction time, because how is the framework aware of which features you're using in the do funds in your pipeline itself? Can the SDK even be put into a portable pipeline graph? How do we serialize that information so that the workers know which features are being used, that the runner knows which features are being used? Can we get it so that the compiler can prevent you from making mistakes entirely? If you watched Byron's Swift Talk SDK, or on the Swift SDK, it turns out with the right language, you absolutely can. But all of this kind of affects also the performance at execution time, because if you have to keep digging down for a language's ability to use reflection or similar, that might have performance implications on how you're trying to call these various methods. So can the SDK even make better choices at execution time based on how we were specifying things? So the challenge I put to myself, I can't even remember how long ago, probably shortly after the last Beam Summit, was, does a Beam SDK even have to look like that with the process element method and start bundle, finish bundle, all that? It's like there's some pedagogical value in these things, but it also kind of might grate against how you would implement some of these things, at least in languages with different affordances. So I started thinking of brainstorming about what I would like a different Go SDK to kind of look like. It would need to make use of generics, so we actually have real KVs. Wouldn't that be a dream? I would not constrain myself to let it look like other SDKs, just to be able to try out new things. Not constrained by compatibility. So what you're seeing today does not interoperate with the existing SDKs at all right now. Although with cross-language, who knows? But also trying to figure out if I can make it so that it was designed for today's Go and also be easier on SDK maintainers like myself, or even make it more encouraging for new contributors to be able to start providing things to an SDK more easily. So let's see what with the main questions I tried to answer, at least in terms of what I'm going to present with this talk. Unlike Byron's talk, where we went through the very deep into the weeds of how the SDK fully does everything, up from user side down through pipeline construction to how everything executes worker side. I'm not going to show off those details because I have a very small amount of time, and it is very deep in the weeds of what we can do in terms of Go. And traditionally, I have not been presenting to a Go forward audience at the Beam Summit. So, but let's see where we get to with these various questions. So if you are not familiar with the Go programming language, there's going to be a bunch of Go. So let's just quickly summarize little things that look a little bit different. Types are specified after the names. So it might look a little bit reversed from what you're used to from Python and Java. Function return types are also similarly after the parameter types. This just kind of follows from the point above. And unlike many languages, generic type parameters are specified with square brackets. They're not necessarily using a map index or a slice index or an array index in that case. That is, they're using type, those are type parameters when specified as part of the function or type definition. So what I came up with, for the most part, kind of looks fairly similar to what we already have in terms of making a structural do-fund today, where you can have some kind of serializable configuration as part of the do_fun struct, it still needs to be an exported type field, which I didn't outline before, but capitalized letters in Go are significant and indicate whether something is basically private or public, or well, closer to protected or public. Otherwise, various Beam features are entirely built on the fields itself. So side inputs can have their access, or the way you access them, whether it is like an iterator or a map, part of the type, along with their specific ability to, or their specific types that they're dealing with. For example, if you're trying to look up int keys with the string values and similar counters, you can have counters. Output types or emitters also become fields in this specific model where we statically type them, and there's a method on top of that in order to actually emit things downstream. But also types for specialized features, which in this case I call out on finish bundle, which is what currently I have as the finish bundle construct, and you'll see why in a second. But I think the most groundbreaking change from what I was trying to do was actually trying to just get rid of the process element method. One of these little secret things under the hood for Beam is that when you're executing things, everything is actually in the context of a bundle, which is an arbitrary sized set of elements that the runner has dictated outside of your SDK. So I wondered, what happens if we just expose that fairly directly into what the user writes? And that kind of led into something like this. So a user would write a process bundle method where it would take in a very specific Beam type. So this allows the SDK to use a generic Go interface to say, if you have a process bundle method with this beam.dfc parameter, then you are a do_fun that is processing that type for, like in this case, a string. DFC in this case, because Go abhors very long names, just means do_fun context. But some nice things fall out of this particular approach. Instead of having a start bundle call where you have to initialize things on a field inside your do_fun struct in order to be able to handle it, and then have to possibly clean things up and null things out so that the garbage collector will take it away in an on-finish bundle, by putting everything into the process bundle instead in a lighting start bundle, any variables you do can be just for whatever processing state or bundling or batching that you want to be able to do, caching, can just be part of the closure that you're then passing into the DFC's process method, which, although it looks like it's actually going to be processing the loop of elements there, is actually just registering a callback that will be executed after the fact. I'm a little uncertain if that's the best way, but it is what I came up with so far. But if you do need to do some finalized things, or after all the bundle elements have been processed, you can use the onBundle finish feature to register a separate callback to do that finish bundle work. But otherwise, once all these methods and such have been nilled out by the execution of the process, any of the state you've declared and created in process bundle will be automatically garbage collected away by the garbage collector without you needing to do explicit nilling of fields and remembering to do these things, avoiding terrible memory leaks. Overall, the features are unified by using a field-based design. This allows everything to be accessible via reflection to the actual framework, which gives us those affordances of, I'm using this side input with this specific access pattern. Great, that is like, it will just have that populated there. Right now, I only have statically defined counters and distributions of various metrics, but there's no reason what I have here can't do the dynamic metrics that we are used to. It's just what I have right now. Similarly, state and timers would also be based on fields inside your do_fun struct. This is not dissimilar to how things are done in Python and Java, for example, where it's usually just an identifier that's happening. The main difference here is that for your on-timer callbacks, you'd simply be registering a callback on that particular field itself, with the name just automatically inferred from the field name in your struct. Outputs, you emit out via this beam output structure. Again, not married to the name, but you would call emit on that to pass things down. But one novel thing I found was that You could make it so that even you can do a bunch of dynamic pipeline construction time things by just making these things a slice or even a map. So at construction time, I can basically emulate partition by allocating a slice of these outputs that can be then determined and used at execution time. And the system will just create things appropriately. Same thing if it was a map, so you could use string keys to emit down. Otherwise, there's also various features for like observing windows, which if you observe a window or use a side input within a DoFun, this prevents optimizations during standard execution because you have to explode all windows out in your processing. You can't combine all these transforms all together. But the important thing here is all the user intent is specified ahead of time and in a way that is observable by the framework. Combiners needed to look a little bit uglier in this case because I wanted to continue to make things work, but it also kind of teaches users a little bit more about how Beam does combiner lifting. So there's still the similar kind of restraints. There's always a merge accumulators method, but if you can also have selectively an add input or an extract input output or both in order to produce out the different variants on these things. So these would need to be explicitly specified when you're adding it to the pipeline or whatever is wrapping these things. But the idea here would be to make it so that these can be used for both combine per key when the value type matches what the combiner is doing, or combine globally if the entire type matches the combiner input and output types. So I was very curious to see if I could achieve compile time type safety. Like I said, I was very annoyed by how the current SDK requires me to rewrite a type checker. Basically, this largely entails us needing to know the element types in the processing method properly and be able to validate the output types correctly and have all this available to the compiler. Pipeline construction ultimately then kind of fell out and looked like this. Everything is happening in this beam run method. You would pass in basically a function. In this case, I'm just using an anonymous function here that receives a beam.scope, similarly to how the current SDK does things. But then you do your pipeline construction within this function. This has kind of been inspired by a document Robert Bradshaw wrote several years ago called Pipelines Are Considered Harmful or something similar. But it's mostly because the pipeline object is very easy to kind of forget. You already have the intent of running the pipeline. So passing how you're building the pipeline to something that is going to run it seemed like a better idea. But this allows you to have like an inline pipeline construction or even a separate function that will build the whole pipeline for you. If you look very carefully, let's see, So if you have some kind of DoFun here, you can set whatever configuration you like. Oh, I have a typo in this slide, but besides the point, what ends up getting returned out from the Beam Pardus is actually the same type that you're putting in. So all the P collection, I've done away basically with the P collection type entirely in this case. The P collection type is basically represented by an initialized version of the output field, which represents how you connect things together. So this leads to a kind of very natural graph construction where how things are consuming different fields, it just kind of falls out naturally from it. I did figure out a way of making it so that we could use anonymous functions inside pipeline construction itself. That was simplified by just having also just kind of like how Beam Python does and TypeScript, just having a actual map construction that just returns an output type by itself. And Pardus and the pipeline itself can also just take in generic or the various option structs in order to provide kind of additional static metadata configuration. So if you wanted to name things so that they show up better than what the default would be, you could provide that and it would be available in the pipeline graph. Similarly, pipeline options could be passed in as part of this whole approach. The end goal, I didn't quite implement this in time for this talk, but would be to have kind of operational options where you would say, pass in a function that produces a serializable type And that would be called as part of pipeline construction. The result of that would be available to this pipeline construction time thing. So you could use that as part of your pipeline construction, but also it would be serialized as part of pipeline options so that it would go on and be available. But similarly, you could see the converse. You're providing functions that are only needing to produce dynamic configuration. So they're only built worker side. Workers, I don't have a lot of time to get into how workers work, but basically the way we handle the generics and avoiding registration, because we don't have a lot of compile time facilities in Go, it's kind of just antithetical to how Go processes things. But we basically redo pipeline construction by having those separated options and construction, separating at how things are built and serializing things effectively. We can ensure relatively deterministic pipeline construction and still be able to access all the types without the user explicitly re-registering things, which is a little bit of a belabored process. Splittable do funds, because I did ask this question for the Swift SDK. I did figure out and implement splittable do funds. They're hideous, absolutely hideous. I don't like them, but I've got something that works for now. But the best part about being an experimental hobby SDK is I'm not married to the final design, but we'll see how long this sticks around. Future work, I want to be able to actually submit jobs to Dataflow right now. Everything works in Docker. I just haven't gone through the full Dataflow submission mechanism because that's a lot of code to copy. I don't actually have state and timer support yet, so there's some details around there. And I haven't implemented windowing strategy and triggers, although that information is passed down in execution time right now. But that's part of just graph construction. So to answer those questions I had quickly is like, can we make the user surface API small? Yes. Can we have compile time type safety? Yes. Can we reduce the burden of graph construction? A little. But we also avoid registering the do funds and enable anonymous functions and closures. So we know what a Beam SDK looks like, right? You have some way of processing all the elements in a bundle. You can do stuff before the bundle processing. You can do stuff after the bundle processing. You can configure and access all the various features and metadata that you want. You have some way of connecting things together into a processing graph, and you can make some lightweight Lambda functions. Bing, bang, boom, Beam SDK. Thank you very much.